So good afternoon. So today's topic is application of InSAR for crustal deformation and the slope stability. So if you see, there are different types of the activities, especially the anthropogenic activities which are happening on the earth surface. Anthropogenic activities like landscaping, tunneling activities, mining, groundwater extraction, etc. So, because of these anthropogenic activities, so many geometrical changes are happening on the earth surface in the form of the translation and the deformation. Okay, and the examples of these changes or applications will be basically the land motion, like the land subsidence, landslide, and land deformation like earthquake deformation, volcanic eruption, infrastructural deformations like dam tilting, bridge damage, building damage, etc. And others are also there like faults and the cracks, plate tectonic movements, glacier melting, etc. Okay, so these activities are basically resulting into the crustal deformation. And if hilly terrain is there, then the slope movement or slope failure phenomena are also there, but popularly known as landslides or land motion or the debris flow. Different types of the terms people are using. So the crustal deformation is related to the deformation which is happening on the top layer of the earth surface. So if you see the causes of these main causes of these activities, so the broadly the causes are categorized into two main categories. One is the geological causes and the second one is the man-made causes. So geological causes like carbonate dissolution, natural sediment compaction, dewatering, drainage of the organic soils, earthquakes, liquefaction, crustal deformation, sediments loading, tectonics, biochemical processes happening inside the earth surface, on the earth surface. And most important, the man-made causes like the extraction of the natural resources through mining activities like ores or coal or the salt, etc. They are extracted from the earth surface or the top layer of the earth surface. And the second is like over fluid pumping in the form of the groundwater or the over extraction of the fluid like the petroleum products or the natural gases. So lot of groundwater we are extracting for many purposes, like for irrigation purpose, for the drinking water purpose, or the for the industrial requirements. So all such water we are using, basically the water which is stored in the aquifers inside the earth, so that is basically called the groundwater. So if in excess amount we are extracting it, so what is happening, the land is going slowly downward, or you can say the aquifers are compacting. So this is another cause, but this is man-made, totally man-made, because for our requirement we are extracting the groundwater. And the same way the petroleum oils, petroleum products we are extracting from the underground. Okay, so the top layer of the earth surface is getting deformed, and that is called the land deformation, nothing else. And same way the natural gases is also extracted from the underground. So in the normal form extraction is fine, but if you are extracting beyond the requirement, or you can say in a huge amount you are extracting, then it is resulting into the deformation. Another important cause is the overloading effect, like the consolidation or the construction of the buildings and the dams. Okay, if you see the metropolitan cities, so high rise buildings are there. So high rise building 20-30 floors are there, so huge amount of weight we are putting on the top layer of the earth surface. So because of this overloading effect, the land is going slowly inside, or the elevation of the land surface is going to decrease. So but in the cities the major this problem may be twofold also, like overloading effect is there, at the same time over fluid pumping is also there, like because of the huge population or the industrial requirement, commercial requirements, huge amount of groundwater you are also extracting. So suppose the support which is there on the earth surface from the groundwater side, that you are reducing, and on the other side on top of it you are putting a huge weight. So you can say huge load you are putting. So from both the sides the land is becoming unstable. So you can say the land instability is increasing. So that is resulting into the deformation. And then another cause is the encroachment of the water bodies like the ponds, lakes, etc. So if you go back into the history, the cities or the major towns are basically were situated around the water bodies, okay, like the ponds or the lakes. But as the population increases, so the people have started encroaching, the ponds and the lakes around the cities. So they were started putting, some garbage or the waste material inside the ponds or the lakes. So from the top side, you can see the water body lakes are encroached, but they started thinking like now it is normal land. But in fact that is not the normal land, because if you put again, some construction over that encroached area, then the health of the buildings will be not that much good whatever is there on the stable land. So if you started constructing the buildings over the encroached area, so over a period of time the huge cracks and the tilting in the buildings can be appeared, okay. So that way you can say the deformation is large, or you can say the infrastructure deformation chances are there, especially in the encroachment area. So all such activities are basically the man-made causes. So because of the geological causes as well as the man-made causes, land deformations or the crustal deformation chances are more and more. So it becomes very important where it is happening and how to measure these deformations precisely, okay. And more than that, if you see the importance and the impact of the surface movement, now I am using the term surface movement, that is coming from the deformation, or you can say the translation. So this is basically a linear or non-linear motion of the surface of the earth. So if surface of the earth is moving by any cause, whether geological cause or the man-made cause, so it is very important for many regions to investigate. Like if you see the spatial planning consideration, so whatever the planning of any activities you are doing, whether it is urban planning or the water resource planning, so everywhere you basically you need to understand what kind of the surface movement information is there, or you can say what is the stability of the land over that particular area. So basically the stability of the land becomes very important for any kind of the planning, okay. Then environmental conservations, again it is important, because if surface is not stable, so land can go down or can go up somewhere. So somewhere, water logging problems may appear. Suppose land is going down, so you might be seen in the metropolitan cities during the monsoon season, the water logging problem is there. So that is because of the land is going downward, or elevation is going to decrease. So this is not happening uniformly in the cities. So somewhere it is going, in the large amount, somewhere it is in the less amount. So if it is happening in the reverse direction, means water is flowing in a top elevation to the lower elevation, but this phenomena is happening in the reverse way. So in that case, it may be the problem of the water logging. So from means the water logging problem you can see as a problem of the land surface movement. Whether suppose initially the land movement was somewhere like this, so water can move from this side to this side, but because of the man-made or the natural causes, the subsidence is happening over this particular region. In the cities I am talking about, okay. If subsidence is happening here, it means this is at its original position, but this land is going down. So now see, now the water cannot flow from this side to this side, which means the water logging problem will be there over this particular portion. So these types of the problems will create so many effects in the society or the economy, and okay, and hence the environment. So environmental conservation planning is also there. Then again, infrastructural design and the construction. So everywhere you want to construct something, whether it is warehouse or factory or any commercial setup, or the national highway, or your buildings, etc. So everywhere you basically checking the stability of the land. So people are using constructing the national highway, so civil engineers are going into the field and they are checking the stability of the land. So if land is not stable, so they are not recommending for the construction of the national highway. Same thing is there for every other industrial setup or other things. Okay, for example, you want to construct your house in the city, so again you want to you have your own choices. So you are not constructing your house in the dumping yard or in the encroachment area, something like that. It means you are worrying about the stability of the land. So in the infrastructure design and construction activities, the surface movement information is very, very important. So from the surface movement information, you can just check whether the land is stable or not stable. Same way in the utility networks, like in the cities, we have to construct the drainage system, and then we have to construct the pipeline network for the gas or for the sewerage line or for the water supply. So this is also a kind of the infrastructure. Okay, nowadays people are using the cables, also underground cables. So all such activities you can plan according to the stability of the land. If you are not comfortable or you are not confident that the land is not stable, it means you are not investing your money over that particular area or the city. Okay, same way in the sewerage and the drainage system design, subsurface utility planning, seawater intrusion control, flood mitigation inland as well as the coastal region, then groundwater extraction regulations also. This information is very much important for the regulations for the groundwater related. For example, I can give one example of the Punjab state in India. So that is very the Punjab state has very fertile land, and that is very much suitable for the agricultural activities. So people are basically using huge amount of the groundwater for irrigation purpose. So every year they are basically started taking 2-3 crops per year, or sometimes more than that. So if more crops are there, it means more requirement of the irrigated water is there. So huge amount of water they are exploiting from the underground earth. Okay, so now the groundwater table is going down over a period of time because of such activities. So now there is some restriction from the government side, because government looks all the requirements of the particular state, means they want to satisfy the drinking requirements, industrial requirements, and other requirements also. So they are basically imposing certain regulations, like everybody cannot digging the bore wells for the extracting the groundwater. So such kind of the regulations are there. So these regulations they can formulate if they have the information of the land subsidence or information of the aquifer systems, or in a simple way we can say if they know the information of the land surface movement. That is land subsidence is nothing but the land surface movement itself in the vertical direction. So now you can realize what is the importance of the land surface movement. Okay, then if you see the impact, so impact you can see because this land surface movement is happening, so it can affect the buildings health or the facilities which we have or the infrastructures we have. So if all such things are getting impacted, then it means we have the infrastructural impact. Means land surface movement has the impact on the infrastructure in the form of like cracking of the buildings, tilting, sinking of the buildings, breaking pipeline networks, or the malfunctioning of the sewerage systems, etc., etc. So these all are basically the problems related to the infrastructure. It means if land surface movement is more in a particular area, it means our infrastructure will be getting impacted at a large. Okay, so if infrastructure is getting impacted, it means infrastructure is associated with the money, or you can say the economy. So in itself, in other words, we can say it has the economic impacts also, like increase in the maintenance cost of the facilities or buildings, or the other sewerage systems or pipeline networks, or decrease in the property value. If the property is damaged or no getting impacted, it means the value, property value will also decrease. Then you can say the disruption in the economy. So these are the impacts in the economic angle. So you can say the land surface movement has infrastructural impact and the economic impact. And if economy is impacted, it means the society is also getting impacted. So you can say the social impacts are also there. It means if you are you should spend more money, it means you are also getting impacted. If everything is getting impacted, then environment is also getting impacted, because we will start some other activities by which the environmental losses will also be there. For example, lowering of the quality of the living environment of the life, that is social environment, and disruption of the daily activities of the people, that is social impact. But environmental impact, like the changes in the rivers, canal, and the drainage flow systems, because then the free flow may not be there. So that may create some environmental impact. The frequent inland and the coastal flooding problems may be there because of the land surface movement itself. Then expansion of the inundated areas. So over the inundation over a particular area is increasing over a period of time. It means the things are getting affected more and more if the more land surface movement is there. So that way you can say the environmental, social, economic, and infrastructural impacts they have. So it becomes very important to monitor the land surface movement. So we have already studied in the previous classes, like the SAR remote sensing has the potential to monitor these very slow type of the motions, because these motions means that deformations or the subsidence or the landslides, these are not very fast movements. These are very slow movement, or plate tectonic movement. All are these basically very slow movements which we cannot see from our eyes. So these SAR signals, which are complex in nature, so they have the ability or capability to observe such very slow type of the motions very easily. And over a period of time, all the displacement or the deformations we can calculate. So as I already mentioned earlier, the time series of displacement we can monitor from the differential SAR interferometry or some advanced multi-temporal InSAR technique. So if you have the time series of the displacements, so from that displacement we can calculate the velocity, time series velocity, and then from velocity we can calculate the acceleration. So if we have these kinematic variables, it means we can understand the total kinematics of that particular region. So this kinematic calculations can be done with the help of the InSAR technology. How we can do? I will show you some case studies after this slide. So where we will see how the deformations we can tackle, and how the slope, especially in the hilly terrains, how the slope instability is started and converted or reflected or resulted into the damages or the landslide, or damages maybe in the properties or the lives also. Okay. So here I want to see one case study of the landslide in the Sirmaur district of the Himachal Pradesh in India. So here you can see this is the Sirmaur district of the Himachal Pradesh. So in this district, this national highway 707 is passing. So this is the national highway. So on the 30th July 2021, a huge landslide was happened over this particular area. So that landslide event was captured by certain few reporters also on the ground. So because the continuous movement is happening along this national highway, so you can say that before the landslide the scenario was like this, and during the landslide the pictures were captured by different reporters, media reporters. So you can see this is the national highway, and huge amount of mass was moved from the top elevation to the downward side. So this from here to here, basically this mass has moved from this top location to the this valley. So this distance is around 200 meters. Okay, so this huge mass was getting displaced, or you can say the slope was followed, and the mass, associated mass, was moved towards this side. So this was in the news, and after this event I visited this particular location. So during this my visit I have captured few photographs. So these are the post landslide pictures you can see here. So here from this picture you can see that this slope is very sharp. Okay, so this is not gentle slope. This whatever the mass was there, suddenly it basically moved towards the downward side, so this side. So what I did actually here, because the event was already happened, so the post analysis was carried out using the Sentinel-1 images. So I used basically the ascending and descending data set before the landslide event, and around 2 years data I have used, and using that particular data. So data was taken from 2019 May 2019 to July 2021. So almost 2 years data was there. So that I have used that data, and from that data I have calculated the time series displacement. Means the displacement from May 2019 to July 2021. So how in a different steps the displacement was increased, and hence the velocity was calculated. Okay, so by analyzing the trend of the displacement I have used certain methods. Okay, so because this displacement of velocity is varying over period of time in this particular fashion, then can we predict the landslide using the previous this information. So that prediction of this landslide was also done using the displacement and the velocity information. Okay, so here you can see this methodology was adopted. So the advanced technique called the persistent PSI, or persistent scatter interferometric SAR, that methodology was applied. So here you can see in that SLC images were taken, then orbit files and SRTM DM, then some flowchart was applied over the InSAR scientific computing environment, that is ISC software. So different steps were performed, like this tops splitting, orbit file master selection, co-registration, spectral diversity enhancement, then interprogram generation, debusting, and then stamps export for the PSI analysis. And then in the stamp PS, this is another software, this is another software. So stamp PS analysis was done for the persistent scatter processing, where the number of steps are there, like initial PS candidate selection, then some beading or filtering of the PS candidates, or you can say noisy pixel removal, then phase corrections for the DEM, then 3D phase unwrapping, then deformation and the residual topographic error estimation, then again especially correlated log angle error estimation, and the atmospheric phase screen estimation and removal. So after this, finally the land surface movement time series was observed and finally visualized using the QGIS or the Jupyter Notebook or the RStudio softwares, and the stamp PS visualizer also. So this particular methodology was applied for Sentinel-1 images, and ascending and descending data sets were used. So around 52 images, here you can see 52 images in the ascending data set and 41 images of the descending pass was used, and the data was acquired in the interferometric wide mode. Frequency of the Sentinel-1 is 5.405 gigahertz. So here you can see these are the images, like ascending, descending, So this one green one is showing the ascending data sets. So 11 September 2019 to this 26th July 2021. So data from September 11 2019, sorry, the data was not used from the May June, but it was used from the September 2019 to July 2021. So almost 2 year data. And same thing for the descending, which is from this orange color, 7 September 2019 to 22nd July 2021. So you can say almost 2 years data was used, and the actual landslide event was happened on the July 30th, somewhere here. Okay, so you can say the last scene in the ascending pass was taken on 26th July, and last scene in the descending pass was taken on the 22nd July, and the actual event was happened, on the July 30th. So here you can see, if you count the number of days from 11th September 2019 to 26th September July 2021, so these number of days are around 684. So you can say this is the first day and this is 684th day. So almost similar days are there from 7th July to 22nd 7th September to 22nd July 2021. So almost 684 days, because that is 11 minus 4, so 26 minus 4. So 11 minus 4 is 7, 26 minus 4 is 26. So again, in the both the images or both the passes data sets, we have taken around the investigation period of 684 days. Okay, and the date of each and every image is mentioned in this one, and this red one, this 4 and this first, this is basically the image which was considered as a reference image. So you can say in the ascending pass, the 4th November 2020 image was considered as a reference image, and the 1st September 2020 was considered as a reference image for the descending pass. Okay, so this is the star network for the ascending pass. So here you can say from here to here the data, this is the temporal baseline which we have already seen in the previous lectures, and this side is the perpendicular baseline. Same thing is for the descending data set. So this is the star network for the ascending data set, this is the star network for the descending data set. So these are 52 images, these are 41 images. Okay, so for analysis purpose, I have used the ISC software, Anaconda, Jupyter Notebook, Stampius, Snapu, Triangle software, MATLAB software, Stampius Visualizer, and QGIS software. Okay, so these things were used for the analysis. Now here you can see, then again from the ascending descending data sets, both were coupled together. So just to calculate the vertical and the horizontal vertical and the horizontal components of the displacement vector. So this slide we have already seen in the previous class, because the line of sight displacement we are calculating from each pass. So the velocity from the line of sight velocity from ascending data, line of sight velocity from the descending data is associated with the east west velocity and the up and down velocity. So here you can see this is the horizontal velocity, this is the vertical velocity, and these are the factors depending upon the incidence angle and the azimuth look angle, which are known. So you can say in these are two equations. So these are values are known because the data was analyzed from both the things, and these factors are also known because incidence angle and azimuth look angle are known. So only unknown factors are these horizontal and the vertical velocities, or you can say displacements. Okay, so these are the two equations, two unknowns are there, exactly they can be solved, and both the horizontal and vertical component of the deformation vectors were calculated. So this we have already seen in the previous class. Okay, and this we have already seen because the distribution, spatial distribution from the ascending or the descending pass is not same. So we are resampling over the common grid, so that over each and every pixels we have the line of sight velocity from the ascending as well as from the descending, so that the previous equation can be applied. So if we have the values over each and every pixels, then applying those equations and calculating the horizontal and the vertical displacement or vertical deformations. Okay, so here you can see This is the output of the ascending data set, and these values are shown like the mean line of sight velocity. So you can say this is the landslide area. So number of points were observed in the landslide affected area. So the values are changing from minus 25 millimeter per year to 30 millimeter per year. So the blue colors are representing, the positive displacement, and red colors are representing the negative displacement. Negative means the movement away from the satellite, and the positive means movement towards the satellite. Okay, so here you can say the major mass was moved from this particular portion. So over this particular region we are having the red dots, which means the negative displacement, which displacement. Okay, it means the motion was happened away from the satellite. So, and few points were also downward side, and this analysis is from the ascending data set. So what I did actually, the same thing I have done using the descending pass. So more or less same type of the distributions was received, but the values were varying from minus 22 millimeter per year to around 24 millimeter per year. Okay, so and using both ascending line of sight velocity and descending line of sight velocity, horizontal and the vertical components were also calculated. So whatever you have seen in the previous equations, two equations, the product of those equations are here. Okay, so this is line of sight velocity BLOS-A. This is the line of sight velocity from the ascending pass. BLOS-D means line of sight velocity from the descending pass. Both were combined together, and incidence angle and the azimuth angles were used, and the EW was calculated, that is displacement along the east-west direction, and B up and down. So this is B up and down. Okay, so these were carried out. So here you can say this, the arrow were also represented along the east-west direction. So the movement which is showing here, you can see the most of the displacement is moving towards this side. It means this mass was moved towards this way, and this is the vertical component of the displacement vector. So again this movement is happening towards this side, and these are not going in the upward direction. So these are the outputs. Then what I did actually, using I have picked basically 3 points from this particular region, means 2 points from here and 1 point in the downward side. So this is PS1, that is persistent scatter point number 1, PS2 and PS3, and similar the same points I have picked from the descending data set. So because this is the time series of the displacement, so the time series of the displacement I have investigated from the ascending data set as well as from the descending data set. So the PS1 is somewhere here, but the exact PS1 was not received. So the adjacent point or the surrounding points or closest point was picked from the descending pass just to identify the PS1. So the time series displacement was investigated, and that investigation was used for the prediction of this landslide event. So for that prediction purpose, these two methods I have used. One is the inverse velocity method, and the second one is the modified inverse velocity method. So the first one is the purely graphical method, and the second one is the purely mathematical model. So here you can see the mathematical equation, like 1 upon V equal to 1 upon V naught into 1 minus T0 minus T upon TF minus T. So you can understand like this, 1 upon V, V is the velocity, so 1 upon V is the inverse velocity. That's why in the name itself the inverse velocity term is used. Okay, so this is 1 upon V is the inverse velocity at time t, and 1 upon V0 is the inverse velocity at time t0. So you can say in the displacement time graph we have to identify two times and the corresponding velocities. Okay, so time t and the velocity at t, and time t0 and velocity at time t0. So these 4 things we can investigate from the displacement time series graph, and the TF can be calculated from this equation. Like V V0 T and T0 so what is left only, that is TF. So that is TF is the time of failure, time of slope failure. Okay. Time of slope failure means the landslide can happen at that time. So two velocities and two times, you can predict the time of the actual failure or time of the landslide. Okay, so this is mathematical relationship. And on the other side, this inverse velocity method was also developed by assumption that suppose if you just visualize the landslide event in your mind, so what is happening, this is, let us say, the slope. Let us say this is the terrain and this much is the slope. Okay, so let us say at this time this is stable, but over a period of time this slope is increasing like this. Let us say initially it is here, then over a period of time this is moving like this, so that the slope is increasing. So if this slope is increasing beyond a particular value, then what will happen, the mass which is there, that becomes unstable. So you can say that mass will start moving downwards. So if mass is starting moving downwards, the phenomena is called the landslide. Okay, so and at what time it is happening, if the slope is increasing beyond a particular value. So if it is crossing that particular slope or threshold value, then the mass is going downwards. In that case, the velocity of this mass, initially the velocity was 0, but displacement was increasing slowly. But if it is slope is increasing beyond the threshold, then the velocity of this particular mass landslide is basically very rapidly. So you can say initially the velocity was almost very close to 0, but slope is increasing beyond the threshold, then the velocity suddenly increases very rapidly, which means the graph, if you see, then the graph will look like this. Suppose this side is the displacement and this side is the time. Okay, so if you see, as the time is increasing and this side is the displacement, so as the time is increasing, the displacement is increasing very slowly. Okay, if at a particular time the displacement increased very rapidly, so this rapid movement shows the landslide situation, because when the landslide is happening, it means this displacement will go rapidly, very rapidly. Okay, so initially it was very slow or very close to 0, but at a particular time this displacement increases manifold. So this particular situation is called the situation of the asymptote. Okay, so you can say that we want to identify that particular time, or you can say the time for the asymptote, but the slope is this velocity or displacement is increasing very rapidly. So we are not able to identify very clearly the exact time of the asymptote. So what we can do, we can draw another graph, and this graph was displacement versus time, or you can say the graph is representing the velocity, or in other words you can say this is the velocity versus time graph. But if we draw the inverse velocity versus time graph, then the situation will be different. Suppose this on the y-axis, we are taking the inverse velocity, and on the time axis time is there. So now if we correlate with the landslide situation, so what will happen, initially the inverse velocity is almost very close to 0. When the landslide is happening, then the inverse velocity will go downwards like this way, because velocity is going like this way, means increasing very rapidly, which means the inverse velocity will go downwards. If it is going downwards, it means this particular curve will cut down the time axis somewhere. So wherever it will cut down, that time is the time of the slope value. So just visualize in your mind how we can understand this particular situation. So we are basically plotting the inverse velocity versus time graph, and wherever this curve is cutting or intersecting the time axis, so that particular time is the time of the slope failure or the time of the landslide. Okay, so similar concept was used here. So here you can say this side I have taken time on the time axis, and on the y axis it is inverse velocity. So this graph is not showing the complete behavior. The last few points means the last behavior was visualized over here. So at all those 3 points, PS1, PS2 and PS3. So here you can say this diamond symbol, you can just see here, this is the diamond, this is diamond, diamond, okay, and last points were basically picked. Then what I did, basically I put it, the regression line. So this is basically the regression line, or you can say the best fit line at PS1, and this circle at PS2. So different circles you are able to observe. So the circles are the best fit line for circles is, let us say, this one, okay, and these the squares are the for the PS3. So the best fit line for squares is another one. So now if you see, this is the last image up to where we are having the velocities or the inverse velocities, because in the ascending data it is 26 July 2021, in descending data it is 22nd July 2021. So it means that data is up to here only. So these lines are up to here only. Now if you see that the slope of these lines is continuously decreasing, and if we extrapolate them, or you can say if we extend these lines, so if we extend this line, so this line will cut this time axis somewhere here. Similarly, this line if you want to extend or extrapolate, then it will intersect this time axis somewhere here, and this line if you extrapolate, then this line will cut this time axis somewhere here. So now you see, just point out wherever these 3 lines, whatever we 3 points we have picked, so these 3 lines are intersecting over time axis at different locations. So you can say this one is intersecting over here, and this one is intersecting over here, and another one is intersecting in the middle. So the time from here to here you can consider as a time window for the landslide. Means landslide can happen in between from here to here any time. So that way, instead of telling a particular time, like at 3 o'clock of a particular day the landslide will happen, so instead of saying like this, you can say from Monday to Thursday any day, just like here, means this from here to here, means from Monday to, let us say, Thursday, any day the landslide can happen. So instead of commenting on a particular minute or hour, you can comment the prediction in terms of days, so that a window you can tell, okay, within this window the landslide can happen. Okay, so these 2 concepts were used for the prediction of the landslide. Okay, so here you can see, this is the graph. Here you can see this side is the time, observation time on the x-axis. So 0 means 7th September 2019, and the last image was taken in case of this the descending. So the last image was taken on the 26th July 2021. So this image is the 26th July. So here you can say from 0 to this is around 684. So some things I have already mentioned, like first acquisition 11 September 2019, last acquisition 26 July. So actual failure was happens on 30th July 2021. So from this way if you count, then it is 688th day, means from 0 to 688th day the actual event was happened. So number of scenes I have taken 52. So total observation time from here 11 September 2019 to 26 July 2021 is 684. Okay, so you can say last image is here up to here, that is 684. So now the plotting was done at all 3 points, PS1, PS2 and PS3, and this side was taken the cumulative displacement, time series displacement. So here you can say these are the symbols used, like diamond for PS1, circle for PS2, and square for the PS3 points. Okay, so all graphs were plotted. So here you can say initially, or you can say if you are at the very close to September 11 2019, so the displacement at all 3 points is very close to 0, and it remains 0 for a longer time, but from here some displacement has started, but that is, you can consider as a error part. So it is almost 0, but after this particular period, so you can say this is 300 days. So you can say after 300 days from September 11 2019, or you can say around 400 days from, or 3 total days are 684. So if you subtract 300, it means 384. 384 means almost 1 year before the actual event. So actual event was happened somewhere here. So if you subtract 1 year from here, so it will reach somewhere here only. So you can say from here onwards, the displacement at PS1 has started very rapidly. Here you can see, but the displacement at PS2 and PS3 still remains very close to zero. But after this time, the displacement at these 2 points were also started very rapidly. So now from here you can see the major instability over these points started from this date onwards, or you can say just 1 year before the actual event. So you can say the instability or the displacement at all these 3 points, not only at these three points, I have picked only 3 points, but such situations is similar to other points also. Okay, but this movement shows the instability over the particular region. So you can say this instability started 1 year before the actual event. So then basically this information was used for the prediction purpose, and this information was used like here, this I have already explained. So you can say these last 4-5 points were taken. So you can say this portion was used, or you can say and this portion was again visualized over here, and then the regression line was fitted, and then this the extrapolation was calculated from the time axis. So basically that is telling us the time of prediction. So by this calculation I have observed the inverse velocity method prediction at all these 3 points is 690th day, 686 day and 685 day. So you see the actual event was happened on 688th day, but according to the prediction is the 690, 686 and 685. So you can say these 2 days are coming before the actual event and 690 is coming after the actual event. So you can say the mixed kind of prediction we are getting. So you can say this method is telling from 685th to 690th day, any day the event can happen. So it is basically giving an indirect hint to us that the landslide can happen from 685 to 690th day, any day. So this is basically called the prediction window, and the actual event happened on 688th day. So that way it is correct, because it is telling indirectly the window, prediction window, and within that window the landslide happened. So that way if you see the accuracy, then that way the accuracy is good. Okay, and if you see again critically, so you can see the 685 and 686 is just before the actual event. So people are considering good prediction if prediction is done in advance. So 685 and 686 are basically the advanced kind of prediction. So that way the people are saying this is the safe prediction. So but the 690 is the day after the actual event, means already landslide happens, then you are predicting. So that way the 690 can be considered as a unsafe prediction. But if you see the window, then it is fine. If you see the point wise, then you can categorize the safe or the unsafe predictions. Okay, and the same analysis was done using the modified inverse velocity method. So prediction is like this. So the time t and the velocity at time t, and then we identify the t0, that is onset of acceleration. So acceleration started very rapidly, so that is the time t0, and the velocity at t0. So t0, v0, t and v were calculated from these graphs and put it in this relationship, and tf was calculated, and those days are like this one. Okay, so this way you can say the prediction from both the methods were done. So in this one value is exactly matching with the actual predictions. So similar analysis was carried out using the descending data sets also. So by this way basically we can say the time series deformation analysis is useful for the slope failure or slope stability checking also, because with the help of this behavior itself you can understand whether the landslide can happen over a particular region or not. If the displacement is continuously increasing, it means the slope will increase and there will be a one day where the landslide will happen. Okay. Similarly, I have done another case study over the Josimat town in India, in Chamoli district. So here you can say this is the Chamoli town. So this town is divided into different wards. 9 wards were there. So this region is basically showing, has a very long history of the disasters. Different types of the phenomena are happening, like rainfall, heavy rainfall, cloud burst, flash flood, landslides, land subsidence. So many types of the problems are there over this particular region. Not from recent days. It has a long history actually. Earthquakes are also happening over this particular region. So in 2023, January 2023, there was a nationwide news in India, like the huge cracks in the buildings over the Josimat town have developed. So people were very in problem, and then central government, state government, and district authorities have started, forming certain committees and started taking actions how we can help to the people of this town. So that time I was also processing in my computer the same area. So I also observed the deformation was basically happening in the some portion of this town. So this analysis I have carried out from 2019 to April 2023. So that analysis was carried out using the another multi-temporal InSAR technique, that is SWOS technique. So here you can see, luckily what happens, I was also aware about the region. So I visited this Josimat town in 2020 itself, in April 2022. So that time you can see these types of the cracks I have observed in the town. So these types of the cracks, and this one, and some gaps between the lintel and the walls, and along the roads also some creeping was observed. You can see this creeping, so the land is moving downwards, road is sinking. So such kind of the deformations were already there in the town. Then in January 2023, because of huge cracks, the level of cracks was started manifold. And from one unknown one location, the muddy water was also observed. The source of this muddy water was not known, but the muddy water was observed. So such kind of things I have critically analyzed, and these data sets again from 111 images were used. Okay, from September 2019 to April 2023. Sentinel 1A, 1B images were used. This was the methodology used. Okay, so time series analysis and the time series domain processing was done. So around 424 interprograms were generated. The similar graph we have already seen in the previous lecture. So this is a small baseline configuration. So total 424 images were interprograms were generated. So maximum temporal baseline was 84 days and perpendicular baseline was 262 meter maximum. Okay. So these are the spatial baseline, average spatial coherence, and this is temporal coherence. So, and these are the images or the outputs generated for different after different corrections. So this thing I have already seen yesterday in the tutorial also. So the similar graph you might be seen in the tutorial. Okay, so this is analysis was carried out over the Josimat town. So this is the final map. Here you can see the ward wise analysis was carried out, and this is the location, the cross is the location from where the muddy water was observed. So you can see the redness is not the redness is showing the negative displacement or the subsidence, but no subsidence was observed around this muddy water, but this point was basically showing huge amount of water coming from unknown source. and this plus point is taken as a reference point from all the images, and this solid dot is representing the course station, that is continuously operating reference station, that is basically the GNSS data set. So that data set was also made available from Survey of India during this particular event. So that data I have used just for validating my outputs. So here you can see the red portions and the yellow portions are showing, level of deformation. So wherever the redness is there, it means the high deformation was observed. So here you can see central part of the Sunil and the southern part of the Gandhinagar, southeastern part of the Pika Marwadi, and some portions of the Manohar and the Singhdar wards. So these types of the deformations were observed. Then after the event, one committee was formed, so I was also the part of the committee. So I visited this place, and many other institutions teams were there. So they were basically collecting the rate of or severity of the deformation, and those data sets were also compared with these findings, and those things were perfectly matching this output. So that basically attested the validity of the SOR InSAR results. And these are the time series at different points I have calculated, and these are the velocity. This is showing the velocity, and this is acceleration maps. So you can say the coverage in the velocity is less compared to the displacement, and the coverage in the acceleration is again less than the velocity. So you can say the coverage acceleration is there over the smaller portions, but the significance of acceleration is more, because wherever the redness is there in the acceleration map, this shows these areas are still susceptible or is still riskier in the future. So more actions are required to manage these portions. So and the SWOS InSAR results were compared with the course data set. So here you can see both the results are matching perfectly fine. But this particular window was very sensitive from November 2022 to January 2023. So here you can say the movement of that particular land started very rapidly, and during this particular portion you see here the motion was very rapid. It means this is the portion where this came into the news, and huge cracks were developed in the buildings. And you see, once the stress was released or cracks have developed, then after that, the structures becomes stable, more or less stable at the location of the course station. So in the geological structures, once the stress is released, then they become stable. So similar kind of the behavior we have observed using the SWOS as well as the GNSS data sets. Okay.